my old Arab. I don't know what to do with it. I'm just gonna try to break it. Yeah. I don't know what to do with it. I have a bunch of old laptops that I don't know what to do with. Sell them. Oh yeah, I guess. Dude, sell them. Some of them are so broken and like not worth in Facebook Marketplace.
All right, everybody, the numbers up, so get to doing Leon's homework for him. How are people feeling about the homework so far? When's it due? Next week? Next Tuesday?
5 days.
5 days. Has everybody started the homework?
Yeah.
Is anyone confused about what to do in the homework?
Yes. I don't know how to do the rough chain. I got EIP. That was it.
Yeah.
Okay.
EIP achieved.
I will make sure that I post those videos, although they are already on Echo. Do people get them
I think so.
directly?
Could be.
Yeah, they were on Echo.
Okay, so the answers are in there, in the lab. So if you go to the lab, you can just copy it, basically. Right?
The code itself, or should we just go through the video?
Go through the video and understand what you have to do. It's a basic walkthrough. Right? So if you can follow the video, you should be good to go. If not, Leon will definitely have office hours. And he's got it down. His version works perfectly right now.
No.
Didn't you like start it?
Okay, my rock chain is working. My shellcode is bad.
There you go. He can help you as well.
Use my shellcode.
Don't depend on infrastructure.
Oh, let me put some shellcode in the...
Yeah, the first problem with that homework is the rock chain. That's the first problem. Getting EIP, not a problem. Well, I guess the reverse engineering is not the first problem. Reverse engineering problem is the second problem. The third problem is the continuation of execution. And solving that third problem is reliant on your understanding from the reverse engineering. But the rock chain is kind of boilerplate. Oh man, Leon's looking like a political correspondent today.
Oh, bow tie everywhere.
We gave you a hit man to do it. So we're going to continue on looking at our inline allocators today, and we're going to look at 3 examples. We're going to dig in deeply to a 1996 DL malloc implementation by Doug himself that is entirely contained in a single C file. And then we're going to look at 2 other versions that are direct descendants from it. You'll see exactly how direct they are. The first one is UC libc, which is an embedded library, and we'll be looking at the next generation version, and a version of it that was released in January of 2025. And then after that, we will look at glibc, the current version, the latest version, that was also released in January of this year. And we will hopefully have some time to dig into exactly what the changes that occurred are between 96 and 2025, which you would expect to be vast, but are actually not at all. In the last class, we went over a high-level view of exactly what you needed to do to build an allocator, and then what kind of the very bottom level of optimizations are, why you would do it, and what they help you with. And that is kind of something you will want to do anytime you are looking to reverse engineer something. I'm talking directly to my old self here. Do not get into a reversing experience just reading the code from top to bottom, just reading assembly randomly. The first thing that you need to do is a bunch of research, right? You need to have a pretty good top-level view of what goals that code is accomplishing. You need to figure out what are some actual questions you're trying to answer and go in with a structure, okay? And this should also apply to anyone working on their final project looking for ODE. Do your research first, right? You should know exactly what formats that program accepts. You should know what the goals and requirements of that program are. You should know what the limitations are. What is the programmer focused on when they're building the thing, right? So that's kind of what we went through Tuesday. If we were to look at this source code without having that high-level Tuesday view, it would be a little bit overwhelming. There are places that are more complicated than need to be. There are things that we, as someone who is attacking a program, don't really need to concern ourselves with. And knowing that high-level view and exactly what we want to know kind of gives us a way to work with that admittedly very large source and answer questions without getting overwhelmed. Okay. So because this is kind of a reference implementation, and Doug is a professor, he has really, really good notes in all the code. And as we go and look at the subsequent versions of this, all the way up to 2025, you will see that his notes are still in those versions, often verbatim. Even when there are changes that were made to choices that he made, it is his notes, and then date, this is the change we made and why we made it. So you are still going to be looking at exactly what he's thinking, because the architecture of the thing is not changed at all. Okay? So anyone who is disappointed that we last time were talking about a very old implementation rather than looking at PT-malloc 2 that is current right now, it's the same thing, and it's much easier for you to understand the complicated new version if you understand the high-level structure of the simple version and then kind of look at how it has evolved and why. And it'll help you understand if you are looking at newer versions, like say we had a different type of architecture that has different concerns, or we're looking at an embedded thing that has just a ton of memory but almost no CPU because of power usage restrictions. You can guess, okay, the changes that they're probably going to make are going to be A, B, and C, right? And you can look at those notes and see why people made those decisions. So let's take a look real quick. This why use this malloc node is in all of the source that I have seen of this type. It's not the fastest, not the most space conserving, not the most portable, not the most tunable. But he's made trade-offs that balance those things for the time and place, right? So this is 1996, and so we've got a certain amount of computation. Memory costs a certain amount. There are certain problems that, due to that mix of speed and memory space, you will encounter before other problems, and until you can solve those bottlenecks, looking at any other optimization is not worthwhile, right? I know you guys have not heard the phrase execute the common case fast, but I want to dig it into your head as something that you should never forget as long as you live. Execute the common case fast is the most important thing in all optimization and should inform every good engineer. And what that means is it doesn't matter if you've got a function that takes 10 years to run if it only runs every once in 100 years, right? If a function runs once a second, optimize that one. Even if it's small, even if it's fast, the one that runs the most, if you can get just a little bit more speed out of it, you are really going to speed up everything else, right? So execute the common case fast. Don't execute the edge condition fast. Edge condition's fine. It almost never happens comparatively, right? These notes are very extensive and they are interspersed in here. I'm going to give this file as a read-through for the grad section along with Maleficarum. But we're going to dig into kind of some specific stuff here. We are going to look at today the structures that are used, so you can map them up to what we looked at on the board last time. We're going to walk through the public functions, and the public functions are the functions that you as a programmer call into the library, so malloc and free. We are specifically not going to look at the backing memory functions, and those are the functions where when malloc reaches kind of the end of its road as far as its memory goes, it interacts with the kernel in one of several ways to get memory back. Now that stuff is highly platform and kernel and version dependent, but I will say I did go back and look at how memory mapping occurs and how the BRK works, and there is nothing in any of the 3 versions that hard codes and maps at a certain offset from the libc. That's done by the kernel. If that file stream thing still works, that's a kernel problem and not a libc problem. There's no point where that mmap is given a suggestion for address. It's always no. All right, so the first thing I want to point out here is the notes on what Doug calls vital statistics. We talked about this on Tuesday. This has all been written in 32-bit, which is what you're used to. Somebody else added 64-bit to this implementation later on. So the numbers that you see here are 32-bit, right? So 8-byte pointers add later. But you can see there is an 8-byte alignment. That means anytime you get an allocation, it will be at least on an 8-byte boundary. So it'll be your least significant byte's going to be 0 or 8, period, right? Always going to be the case. This version has sizes of 4 bytes, or actually sizes of 2 bytes, which is why the minimum overhead is 4 or 8. So he's got a limit on how much you can allocate in a single allocation that's smaller than what you see in modern systems. However, the minimum allocation size is still 16 bytes. And it's got to be 16 bytes because when we look at the full header size for a free chunk, it's got 2 sizes of 4 bytes each, and then it's got 2 pointers of 4 bytes each, right? So if we actually tried to allocate less than 16 bytes, we wouldn't be able to even store the header that stores the metadata for it, right? So no matter what, even if you ask for fewer than 16 bytes, you're going to get 16 bytes. Where is the actual? So he discusses why those decisions were made, what your worst case scenarios are when you're asking for size, and then why he made certain decisions on thresholds. Those threshold decisions are going to change significantly between implementations. It's going to be one of the big changes that you see going forward is what is the largest allocation? What's the smallest allocation? What are the bin sizes that we chose? How many bins are in each bin size? That's all going to be specific to how much memory we have on the back end, how much we want to give up in overhead, and how we want to make trade-offs between memory and CPU. And there's going to be a slightly counterintuitive thing here where you're going to do a lot of CPU work in the allocator just so you don't have to ask the kernel to provide you more memory. So when you get new pages from the kernel or the heap, or in your process in any way, they must be zeroed by the kernel, right? If I were to ask for a page and it just mapped me something that somebody else had just used, I would be able to look at the memory from that other process, right? We don't want that to happen. That's going to break one of the promises of virtual memory and the protection of our operating system. And so every time you ask for a page, the kernel has to actually be like, all right, I'm going to go off and zero the thing. Now, modern operating systems will do that kind of lazily, which means if the CPU has a core that's idle right now, it'll go off and just start zeroing memory so that when it asks for something later, it doesn't need to block to do that. Older operating systems are not doing that, especially because a lot of them were assuming one core, right? So at allocation time, the kernel's got to do V0 or memwrite, okay, throughout the whole thing.
Is there ever a reason that you would do a 0 byte allocation? Like, what could you do with that?
Nothing. Yeah, no, there's no reason.
Okay, that's true.
Yeah. Normally, if somebody asks for a 0 byte allocation, it just returns null. Which is,
Okay, that's what I was figuring would make sense.
Yeah. Yep. What was I saying immediately before you asked that question? Oh, zeroing. Okay. And so this works whether you're using mmap or brk to add more pages. It happens when you load a new program. So when you start a program and the loader is giving you VSS space, it's got to zero all that out for this reason. And that's really expensive. And so it is better off for you to spend more time and effort in user space defragmenting and cleaning up memory that you have already used in the program so that the kernel doesn't have to go in 0 pages. Okay? And you'll see a lot of that in here. It was more expensive back in a single processor old operating system than it is nowadays. It's another reason you would make a different decision now than you would have made in the past. Okay? Secondary note, in my program, if I allocate some memory and then I free it and it goes on the free list and I allocate it again, nobody zeroed that memory. Okay? So if you were looking for a peak and you had to use after free, one thing you might do is ask for an allocation of a certain size, that's a string, and then print it out as an uninitialized variable. And whatever memory was in there for the last allocation will be still in there. Until somebody writes over it, it's still used. It's the same for the stack, right? If we run a function, and then we roll the stack back up, ESP comes up again, and we call another function, ESP goes back down, the value from the last function, that's still in there, okay? So the kernel makes us a promise that when we get pages from it, it doesn't have memory from another process, but our process doesn't make that promise to itself, okay? There are ways that you can abuse this for peaks on the heap or on the stack. There are stack painting attacks where if you have a bug where a function uses a local variable uninitialized, it makes an assumption about what's in there, and you have some control over how the program gets run, you can force data to be written what you would like there and either use it as a peak or control of a local variable. It's called a stack painting attack. Okay? So small aside on the promises that are made when you allocate memory. In the source code that we're looking at, there will be heavy use of macros. In system programming in general, there is heavy use of macros. There's reason for that, okay? A lot of the things that we write macros for are small calculations that you're going to make over and over and over again in a source code base. So one example of that is in user space, you get a pointer to a chunk, but the allocator needs to look at 8 bytes before that, right? Because that's where its chunk starts. It's handed user space, 1 in the middle. So if I call free, the very first thing I need to do every single time is subtract 8 from that pointer, okay? And I need to do a little bit of casting to make that correct. And so that's an example of something we'll use a macro for. You'll see macros all over the place for stuff that is subtle. Anytime that there's like a mask or a flag checked, there's a macro to do that. And that is so that every individual programmer working on libc doesn't have to write the thing themselves and have one subtle bug over here that isn't anywhere else. So if there is a bug in a macro, we change it in one place and we fix it. Other things, the reason we don't use a function for this, does anybody have an idea why that might be?
Extra instructions.
Yeah, right? It's the things that are macros are subtle and they're used a lot, but they're very small, right? What we don't want is to call out to another function with all the overhead that entails, do this thing that we're going to do constantly in every function, and then come back. The macro ensures that it's inline, right? You could write a function and specify that it's inline. Your compiler is still going to be making choices about that, and it might not be the right choice.
So when you compile a macro, is it taking the instructions and then just inserting them in replicated versions in each part of the code?
No. No, it actually happens before that. So what happens is there's a preprocessor pass in your compiler. Anytime there's a macro, it actually replaces the text verbatim. And then it turns that text into the abstract syntax tree. So it's not doing compilation and then inlining it, it's actually replacing the text. And you can run your compiler with just the preprocessor pass and see the resultant text. Make sense?
I was just gonna ask, I saw in free before, there was a call to some memory address and then it popped, it moved ESP into ESI and then it returned, and I was wondering if that would have something to do with this.
I'll have to see the example, so if you could show me later, I'll talk about it specifically. So let's take a look at a couple of those macros for real.
That just sounds like one of the PIE thunks that you were talking about before, right?
So here's the thing. I actually thought about this. As soon as she asked that question, I was like, is it? No, funcs aren't inlined. They are called as functions because you're relying on the call itself to give you the information you want.
Right, that makes sense.
Right? So even though it's very small, you're going to call anyway.
Mhm.
And there's no local, so there's no overhead, right?
All right.
The func is probably written by hand as assembly, but it's still called as a function, right?
Okay.
Yeah.
Do you mind just going over like the whole thing, like macros versus functions versus funcs, just like in a row? So like.
Yeah. Okay, that's a good question. So your macro, and let me pull one up here so we can see what we're actually talking about. Should have given myself a line number for a macro for examples.
Yes, sir.
Yeah, so these are all macros that are used to define values. I'm looking for one that's a function. All right, here's one. Now it's 0. So, there we go. That's a great one. There's a dust device. So a macro is a straight text replacement. One of the very first things your compiler will do is a preprocessor pass. Part of that is taking included files and adding them into the start of the program. Wherever you have include, that thing is copied directly in, okay? Another thing that you could do is pound define text as just a straight value. I could pound define true as 1 and 0 as false. So when this first pass of the compiler goes through, every time it says true in all capitals, that's replaced with 1, okay? And so it would be exactly the same as if you had written 1 there. You can also define full functions, right? Inside a malloc, sorry, not a malloc, a macro. And every time that you call malloc copy, this code is plunked right in there in text before it gets to an actual compilation phase, okay? So there's no call out to another function, even though it looks like a function. It's just copy and paste it, right? So a macro is basically a copy and paste of whatever's there. You usually put them in your header files, right? So they can be used everywhere. It makes code both easier to read, but also slightly more obscure because every time you see that macro call, you need to know what it's doing as though it were a function. So that's how a macro works. It's just a copy paste. Straight replacement. And you have actually the ability to put in arguments, and those arguments are going to be text replaced, like search and replace. Okay? This differs from a function, which is compiled as you have seen in its own spot, and it requires a call instruction to get there. It has a return that comes back, right? It's its own stack frame. Whereas a macro is in the stack frame of the function it's called from. And then what was the last one we wanted? A thunk. A thunk is not strongly defined, but tends to be a small section of assembly that performs a task specific to an architecture to provide you some piece of information about the architecture itself. So you will see funcs, or the position-independent code is the one that we've looked at previously, which is basically doing exactly what your shell code is doing to figure out where your strings are. It turns your position-independent code into absolute pointers so that you can reference things that require absolute pointers. You'll see funcs heavily in JITted code to do pretty much similar things. Funcs are generally written by hand in assembly, and they're very small, like 4 or 5 instructions. Right? Is that clear? If you're looking at things that have a lot of funcs, you're probably doing some system programming that's fairly invasive, or you're looking at jitter or some other runtime compilation or virtual machine type of deal. Okay. Is anybody familiar with this programming construction? How about maybe people who refuse to do leak code in interviews? Yeah. This is a copy loop optimization that is.
I mean, isn't this just like, because it's one operation in like a bigger chunk, you could just simply use?
You are relying on a kind of a jump table to provide you an optimization for a copy loop in this case. Okay. Oh, he does call it dust first, yeah. So, okay, so here's a cleaner one. Switch statement is basically acting as a jump table here. And so we don't have to loop for every version of this, right? We talked about people using larger registers to make copies more efficient. This is yet another way that you can do that efficiently.
Do the macros do any like type checking on the arguments?
No, it's straight string replace. Yep. Which is also in some ways another benefit, right? Because if I'm going to cast something that's of multiple types, this is a great way to do it. Right? N bytes. Yeah, so like there's no typing on N bytes here. Where's chart used? Automatically cast on chart, so it doesn't matter what type chart is. The very first thing it does is cast it, right? So
we have a lot of macros at work where the first argument is actually a type. So it lets us go through and write macros about generic types.
Yep.
So it's really nice.
So that is a way that you would add standard template library functionality to C, which is actually how STL is written, is macros that take typing, right? So yeah, macro use everywhere. I'll have some specific ones pointed out later. So, all right, let's take a look at what those top level structures look like that we talked about at the top of chunks and also at the top of arenas. In this allocator, there's no concept of an arena. There's basically one default arena, one default heap that's always used. And when we get into the red-based stuff, I'll show you that there are multiples of these, and you can specify them. Let's see. Yeah, here we go. So out of line of where you are performing your allocations, there's a structure that stores a bunch of the information that the allocator needs about the heap itself. Now, this could be in just .data, because in this allocator, there's only one heap. We're never going to need multiples of these, so I could just put it as a global and have this store all the information. It's going to store how much space we currently have, how much space is currently used, how many chunks we've used, how many free chunks we have, all the stuff that it needs to make a calculation on whether to ask the kernel for more space or to give space back to the kernel, okay? Even this structure, as we get more complicated, you'll see there are some things in here where Doug has said, well, I'm going to store this data, but I'm never going to actually use it because I'm not going to make significant changes to how this thing runs based on what I see. In the future, these things that are unused become used. They are used to make decisions about how much space, how much slush space do I want to keep a hold of, right? And when I say slush space, what I mean is, let's say we're making a bunch of allocations, and then we free a bunch of stuff, and we've got this big chunk of totally free space. We may make the decision that we want to hand that contiguous free space, those pages, back to the kernel, and shrink the size of our process. But what we also want to know is, how often do I shrink a bunch and then grow again immediately? Because it would be stupid for us to shrink a bunch and then have the kernel have to zero everything before it hands it back to us immediately afterwards, right? So we would want to keep some profiling data to decide how much slush space do I want to keep. If I end up with like 3 gig of space, maybe I give some of that back, but I'm going to want to keep enough so that I don't have to immediately ask for it again, right? And these are the sorts of extra data that you would want to kind of make those decisions. Okay. This guy here is a doubly linked list of the pages that the kernel has mapped. Okay. A couple of things to note here. What's the first element in the linked list?
Next.
It's next. When we do an add, what order is it? It's constant, right? It's a head add. Okay. And it's significantly more simple than you would expect this data structure code to be, right? Very straightforward. And then let's look at the biggie here. Here's the malloc chunk header. Okay. So when Doug writes his structure, this is the structure that lives at the head of every single chunk that gets handed to you. When you get handed a pointer, the pointer is right here. Okay? This is only used when you are not using the pointer. When the allocator has control of it, because it's free and no one else should be using it, this whole structure is made use of. Otherwise, it only uses this, right? And everything down here you get control of. You could write this differently with using multiple structures that are nested. That's not how he does it. He just writes it there and knows in a certain state these things are valid, in another state they're not valid, right? So, unless I'm wrong, I think Rust probably wouldn't let you do that.
Yeah, it would be unhappy.
Probably would not let you. What you probably need is what, an enum that has multiple types as the secondary portion? Yeah, which would be extremely obnoxious and much harder to read. And the way that we don't screw this up is we use macros to work with it, right? As long as a smart person's written the macro, you can hand that macro to a less smart person, and then that gets screwed up.
The secondary ones could just be like options, right?
No, you would have an enum with one of them basically being a giant chunk of, like a pointer to a giant chunk, or you would have an enum. The other option would be an enum with FD and BK in it.
Yeah, but that gets implemented under the hood as a fact union interest.
Yeah, I mean, so an enum would tell you which of the unions you were selecting at any given moment, right?
Yeah.
So, yeah, union with an enum.
And then use the great.
Is anybody familiar with what unions are? A union is a structure that can be one of two things, and you are able to select which of the type is in the same spot by making a decision, usually with an enum, and an enum is a variable that is limited to a set of numbers, and those numbers are provided names, right? So type 1, 0, type 2, 1, type 3, 2. Those are the only values that enum will be allowed to have, and each one of those corresponds to an element of the union. And at any given moment, the memory could be one of those types. Okay? So another type of structure that people will have used to allow you to do templating and object-oriented work in C. Okay? There is nothing that you can do in C++ that you can't do in C, because all of the functionality of C++, especially the templated functionality, all the object-oriented stuff, is written under the hood in C. If you look up how new works, it calls malloc. If you look up how templates work, there are macros in C, right? So you can do all of it. You'll get less explicit checking by your compiler, but you can do all of it, and people do all of it. And in systems programming, people tend to use simpler constructs that mimic the more complicated ones that they have done themselves, because the more complicated versions are more generic, and so they are less optimal in most situations, right? Providing someone with full templating power means that you have to be prepared for when they use full templating power. If I'm limiting you to only the templating power I want you to have, I can be more efficient because I can make assumptions on how the code works. But that's what we drew up here in red. You can see it's straight up. Second, we'll talk about flags. Should have macros right below. Doug's got some great drawings in both free and non-free state. We drew this sideways. He's drawing it up and down. Other note, he's drawing it low to high at the bottom, which is the opposite of how you draw your stack. It's a little bit more intuitive, but if you were to look at it in memory, it would be the other way around. Right? Here is great commentary and drawing of the free state. This version has got our in-use flags in the my size, not in the previous size. That's a distinction that is not necessary, but you may see it in either way, where all your flags live in your previous size or in your current size.
Why is it upside down when you look at it in memory?
So the way he's drawn it is this is offset 0, and this is offset n, right? When we draw our stacks, we draw the low address on the bottom. So this drawing is reversed how you would.
But the heap's growing down, right?
We don't tend to think of the heap growing in a direction because it's kind of random access. Does that make sense? So in the sense of like calling BRK to get more space, you are generally growing upward, not downward, right?
It goes to a lower memory address then?
So if I start my heap at 1,000, okay, and the end is at 2K, and I call BRK with an address, I'm going to have to call it with 3K in order to get another page. So we're kind of growing up, but for you as a user, you're getting random pieces of it, so you're not really thinking of it as growing in a direction, unless your goal is to make the heap abut some other structure, which is possible in some operating systems and architectures and not in others. One of the benefits to having a larger pointer space is that you can set guard pages, which mean that I'm going to say if my heap starts at 1K and I don't want this process to grow past 3 gig, at the 3 gig mark, I'm going to put another page in here, or just in the page table, a guard page that has no permissions on it. And if my heap hits that guard page, then I say I can't grow anymore. I hand back no memory for an error. And then if someone tries to write into it, I can't write into the next thing. Like say my next map page is a .data section. That guard page will stop me from writing into it unless I have something like you experienced in the second homework example from the first homework where I can pick an index, right? That would allow me to do that. If I don't have 64 bits of pointer space, then I have significantly fewer pages that I can map per process, and losing them to a guard page is not always advantageous. Other thing that he does here, which is interesting, and you wouldn't be able to do in Rust, is he thinks about the start of the next chunk, which will always exist, as being the footer of the object he's got. Okay? So when you make a change to one of these chunks, because you have your size and the previous size, if I change this chunk because I cut it or I consolidate it, I also have to make a change to the prev size of the next chunk, right? And rather than looking at that as its own object, I can say, because I know the distance from here to here, this is essentially a footer of myself, right? And so I'll have a macro that says, hand me the footer. Okay, it does the math for you. Or like, probably what there is a macro that says modify the footer, and it will just automatically plunk that new number in there. I'm actually fairly certain that it is. And I should have written down the address of it. This is a big file, so. Alignment, alignment, shot. All right, so here's actually another fairly interesting macro where if I provide a size to allocate, it will automatically do the math to make sure that I get a valid aligned page that's a multiple of my size, which is 16 on this architecture. It'll automatically do that math to hand me back a correct size that makes sense for the allocator, rather than me having to do that math every single time somebody provides a size, right? If you try to allocate 15 bytes, it's going to be like, nah, you're actually getting 16 bytes, right? If I try to allocate 17 bytes, it's going to be, nah, you're actually getting 32 bytes, right? You'll always be aligned by this macro. Anytime a user gives it a size, it automatically gets translated into a size that makes sense, so that everything's coherent. Okay? Let's take a look at the look-aside lists and the decisions that Doug has made in 1996 for Linux 2.4 kernel. And then keep these decisions in mind for when we get to the end of class, because we'll contrast them with the decisions made for more modern systems. And then later, we will contrast them with the decisions made for JEmalloc, which works very look-aside list heavy. So the decisions are interesting. You get the smaller your bin is, the more you hold. So he's making the assumption that small allocations are far more common than large allocations in this state. And he's saying, these are the powers that I'm going to work with, and I assume that he has done a fair bit of profiling at the time to make these decisions, right? It would be very easy for you to, let's say, add a printf to the malloc function that prints you a graph of how often a certain program asks for a certain size. Graph that, and then make your decisions on where these bins should be based on that, right? And so if I have like Firefox, which writes its own allocator, and I were a Firefox developer, one of the pieces of information I would ask to be sent back when you click the Please Spy on Me Firefox button is, how often am I asking for allocations of a certain size? How often is a bin empty when I ask for it? And I would use that to tailor this specifically to Firefox itself, right? Because it's always asking for objects of a certain type, because the JavaScript interpreter is always asking for objects of a certain type, of a certain size, I'll be able to profile that and make these decisions. The distinction here in the look-aside list is that there are small bins and fast bins. Small bins are never cut. Okay, they are always going to maintain the size they are, and they are that way because we assume it would be, it's not actually advantageous for us to do the work to cut and consolidate them, because we're always going to be asking for these small sizes. When we get to the fast bins, which are of a larger size, they're going to be kind of a greedy first fit. So I'm going to take the very next chunk that is at least large enough for what I've asked for, and if it's significantly larger than what I've asked for, I'm going to make a cut and take what's left and dump it into one of the small bins or another fast bin, depending on what kind of cut needs to be made, right? There's a lot of complication and CPU work that's added and overhead size that's added even at this stage just to prevent you from asking the kernel for more memory, right? They go to a great deal of trouble to stop you from asking the kernel for stuff. And on a machine that's got one core, anytime you ask the kernel for a page of memory, you've blocked for that writing for everybody, right? All the programs that are running all have to wait for the kernel to zero that page. All right, so let's dig into the actual malloc implementation. We're going to dig into the two pieces, malloc and free, and we're going to look at some of the macros that they make use of. So once again, Doug's got some excellent notes that transfer pretty well. We're going to check the bins to see if we've got something that's dead on. If not, we'll pick the fast bin and try to find something that fits and then cut if we need to. And then past that, we'll do the full sweep over our free doubly linked list to find something. Now, there's a lot of optimization that's done on the top chunk, and the top chunk is actually going to be optimized even harder on newer versions. The top chunk is the very last thing that we've asked for in our heap address-wise, because if we can move that down, we can possibly hand a bunch of that memory back to the kernel, right? And that's because we need contiguous space at the end of our heap to return stuff back to the kernel. For long-running programs, we're going to want to do a little bit more work to stop it from just growing indefinitely, right? And so we keep track of how things are looking at the top end of the heap, and there's some complication in here for that. That's not something that you, as someone attacking either a program or the heap itself, will need to care about. But you should be aware of it so that you, when you are scanning through the code, you can say, okay, this is not a part that I need to reverse engineer and really understand. I can skip over that and look for the thing I'm really looking for, right? All right, so the very first thing we see is that request a size macro. Regardless of what we've asked for, it's got to be made into a valid size chunk. And then we make a decision whether our chunk is going to be within the small bins or within a large bin. If it's in the small bin, we do that scan for an exact match. And if we find the match, we see our first use of an unlink. Right? We'll take a look at that unlink function. It's actually, in this case, a macro, and it is a macro so that it can be used generically every time there's a doubly linked list. This thing is made of like 5 or 6 doubly linked lists that we've seen, right? We could write an unlink for each one of them, or we can have a small, fast, generic macro that will take all the information necessary to remove something from a generic doubly linked list and just use that over and over again. Right? This also means that if, say, in a new version of this, you wanted to put a chain validation in where I make sure that my next previous points at me and my previous next also points at me so that I can't do an unlink attack, I only have to put that check in one spot in the macro. Otherwise, there may be places, if you write all this by hand and then you decide you want to add those checks, very often people will write the check for 2 places and miss the 3rd or the 5th because they didn't write it in the boilerplate style, so when the person went looking for unlinks, they missed that one, right? This is another reason why code standardization is kind of important. If you write the same code in different ways in 3 places, and then someone is like, you have a bug in the way that you thought about that, okay, now you got to go find all the places manually. If you don't have boilerplate, you're not going to be able to search them, right?
I've seen a lot of macros poking around the code for the like final project, where they were using it to like safely loop over like lists or like arrays of things. And I just noticed that like constantly with different projects I jumped to.
Yeah. It's going to be very common, right? And being able to recognize that and read it not as individual instructions, but read it as a sentence and see that construct and be like, I know what's happening here. I instantly know I'm dealing with a linked list. This object is in a linked list. Okay, so another point about these linked lists that are here, they are not storing for you, they're not the only place that you are storing access to a pointer. They are storing all of the objects that are in a given state, right? If I remove this guy, because I've allocated it, I removed it from the free list, I'm not removing the chunk. That's still there, it's not getting free. All that's happening is I'm changing the state of the object, and I'm saying I had kept a list of everything that was in a certain state. It's no longer in that state, I get to pull it out now, right? It's another reason that Stefan had asked the question, well, if I screwed up all the pointers, how do I get to this object? This is not the only way you get to the object. This is just a list of things that happen to be in a certain state. You get to that object through a different way, it still may be at state change, removed from a list of things in that state. That's very often how this stuff comes across, and why you see multiple linked list headers in the same object if the object is complicated. It may or may not be in a certain state, which means it may or may not be in any number of a list, right? And each one of those could be in multiple lists at the same time. So you'll see a lot of headers, and you will also see, oh, I got a pointer to something, and then I subtracted a fixed amount from it. Like I subtracted 100 hex from this pointer. Well, how do I know what's 100 hex behind that? It's because I know the list I'm sorting through is 100 from this top of the structure that I'm looking at. I really wanted the structure, even though I'm running through the list as though the next pointer was the fronter, right? And a lot of disassemblers have a lot of trouble with that. Getting it to look proper, especially if you use a decompiler, is a pain in the butt. Okay, so here's what happens if we have a large bin. The difference here between your large bin and your small bin, or your fast bin and your small bin, is that we're going to be checking to see if there is a remainder size, which means I wanted X amount. I had way more than that. Is the remainder large enough that it's worthwhile me cutting that chunk and doing some extra work? The extra work being creating a whole new header, adding something else to a free list, all of that, right? That all gets done if the remainder size is larger than the absolute minimum size for a chunk, right? More work. And then there's our remainder work, right? If we did a cut, we've got to do a whole bunch of work. It's got to get added to a bunch of lists. It's got to be added to free lists. We've got to create a new header. Those new headers in use flags all need to be updated. All this stuff has to happen. Set head and set foot are also macros in this case that are referencing from your top. But that's a lot of overhead to do a cut, right? The final thing here is if it's above a certain size, we're going to actually, let's see, still adding remainders. So all of this work here that I'm scanning through is it deciding where it is in your mapping. This is it deciding if it's worthwhile to return things back to the kernel. That's why it's referencing the top chunk. And here it's deciding if it is larger than a certain threshold, rather than using a normal chunk, use mmap. So there's an optimization that exists on newer operating systems a little bit more than here, where If you are much larger than a page, use mmap to get the thing. It means that you need to have more flags, right? If I have a chunk that I'm going to free back, I need to know, is this part of the normal heap? Was it mmapped because it was above a certain size? If so, I can't relink it back into the normal heap. I've got to make that distinction, which means that now I've got more flags sitting on my current size, which also means that the granularity of my chunk is less than it would be otherwise. So, these are all trade-offs that you would make based on your bit width, your architecture, speed of your kernel, all of these things.
Why can't you add it back into the pool if it came from an mmap?
So, generally, you've got this contiguous space, which is your standard arena or pool. But if you're going to ask for a huge chunk of memory, something much larger than several pages, you're going to mmap that.
Right.
That's not going to be contiguous with the rest of it.
Gotcha. Okay, so when you're doing that mmap, you wouldn't request like the basic or the address to be like at the end of your current arena.
No, because then you'd
make your next ones not contiguous.
Yeah, or if you call BRK again, it would overlap your mmap, which would be a problem, right? It wouldn't work. So when you do an mmap, it's off somewhere else in space. Theoretically, it should be a random number, although it seems to be that it's some fixed offset from libc, based on how the kernel is working right now. But the whole heap relies on the fact that that memory is contiguous, right? For me to say, oh, I'm going to look at the footer of this means that I must know that my next heap chunk abuts the current one. My data structure, unlike a typical linked list where you don't have to make assumptions about where things are in memory, is reliant on the fact that this is contiguous memory, and all of that contiguous memory that is within the heap is within one chunk or another, right? It's either going to be consolidated back into a large one, it's going to be a small piece, but there's no space in there that there is a gap, and if there were, I wouldn't be able to walk that properly, right? Anytime that you make a linked list or a structure like a linked list, like a tree, you can always save space by actually making it an array that you are storing information about, right? Like if I take a binary tree, I can always compress that down into an array. Well, I'd have to shift everything over, but like this guy comes here, and this guy comes here, and this guy comes here, and this guy comes here, this guy comes here in the array, and I can do, just math to figure out which is which, right? And that's kind of what we're relying on for this data structure.
So if you have an event that causes you to allocate like do a bunch of like tiny allocations, which means you have to get more pages, you really can only clear that from the back forwards. Okay, so it's probably really hard to actually return the pages back to the kernel.
Not necessarily, because even with ASLR, it's still giving you contiguous space.
Right. What I mean is like it only takes one still active pointer somewhere in the back to mean that you can't clear all these pages ahead of it.
Yeah, unless you had a sweeping algorithm that moved it, which would be extremely obnoxious and require garbage collection and a bunch of other stuff to fix up all the pointers, right? So you'd have to have like some other structure sitting on top, so like Java could do it.
Right. Or you'd have to say, I'm giving you a pointer to a pointer, and then you can move the underline.
It's extremely obnoxious and not common, but yes, you're correct, right? Like the giving back from the top chunk kind of relies on something like I'm a server and I'm serving 5 users, and when I serve a user, I create a bunch of space.
Yep.
I give that back. If it's my last user, I can give that back, right? So scenarios like that, right? Where you're not as interspersed as you expect.
That makes sense.
Yeah. But if I had a web server and during the day I served thousands and thousands of requests, and then at 6 o'clock at night when people went home from work, I served no requests, it would be very easy for me to hand all that back tomorrow, right? If I want a billion years of uptime, that's the one way to get it. Yeah. Let's look at free. That unlinked macro that was used in both malloc and will be used again in free is generic, right? It takes 3 arguments. It is the pointer to the object we're concerned about, the name of the back pointer, and the name of the forward pointer. And it is going to handle all of that, right? It just does text replace to make that into its unlinked algorithm, okay? Once again, that chunk doesn't go away just because it's been removed from a list. It's just changing state. And so it no longer lives in the list of things within that state, whether that's our free state, whether it's in use, whether it's a bin. So the free implementation, we're going to skip over a fair bit of it right at the top because it's going to look at whether or not the top chunk needs to return things back to the kernel, whether or not we're using huge allocations that are backed by mmap. And we'll hop right to what happens when we free a normal size chunk. Right, so we're skipping 1, 2, and 3 here. Whether it's mmap, whether it's in the top chunk, and we're going to consolidate and remove things. Malloc trim is what returns stuff back to the kernel. We're going to go look at normal chunks that are either consolidated or placed into bins. There's an optimization here, last remainder. We'll talk briefly about, but I don't want to get into it. So on a free, this mem to chunk macro just subtracts 8, or the first part of the header size, from the pointer, so we can get our actual chunk from that pointer. Here's our consolidate backwards. That's top chunk allocation. Consolidate backwards. Okay, so here's a normal chunk consolidate backwards. First off, we check to see if the previous one's in use, and we deal with creating the size that they will be once we put them backwards together, and then we remove it from the free list, right? So we always check the chunk before us first, which means that the question that Stefan asked last class is absolutely correct. You can put your, if you're going to do an unlink attack, you can put your fake object either in the chunk behind you or in front of you, and putting it behind you will get you your right earlier, which may or may not be advantageous. But rather than doing it all at once and saying, oh, if I have some on both sides, I do the consolidate together, it does it one at a time. So the back one first. If my previous is not in use, then I can put them together. Then I check if my next one is in use. If that's not in use, I can put that together too. Okay? And both of those use that same macro, and they do some fairly simple math to decide, am I the last chunk? Am I going to hand something back to the kernel? What's my new size going to be? It's my size plus my previous size, and my size plus my next size. And that is that for our freeze. Okay, so let's look at, let's go in and look at some other implementations for this.
The unlink, if there's an unlink before, like the chunk above the one being freed is going to be consolidated with the one being freed, and you try to do the unlink bug with the chunk within the one that's going to be freed. If the chunk before is free, won't that like clobber the fake chunk headers that you set up inside the chunk to be freed? Because now the headers are going to be higher up versus before?
No. So here's why. There never could be, as far as the algorithm is concerned, two contiguous chunks that are free that have not been consolidated in this scenario. So if I had these two chunks and I whacked this header and I make a fake one here and then I free this one right here, it's only going to look back where I tell it to. It's never going to look back here to do a consolidation, right?
I think if you make the fake chunk below the gradient header.
Yeah. So here's our fake.
Oh wait, which one's higher memory address?
Let's call this 2 and this 1. So this is higher.
Okay, yeah. So if you had the fake chunk inside the higher memory address, and then the one above was freed.
This one here?
No, the lower memory address was freed. And there was no fake chunk. When it scans forward for forward consolidation, wouldn't it not? It would go forward what it thinks the total size is and not hit that next chunk, right?
After it consolidated these two together. I'd have to look. My guess is no, and because I've already clobbered this with a fake size that's smaller, so when it does the add, it's still going to think the boundary's here because I hit the my size. I don't know for sure because I haven't done it, but that's what the brain says. And I am sure that there are, implementations or variants on this for which it will or will not work. And it depends on how it was implemented. However, because these are direct riffs,
This file's too small, doesn't have my 600.
yeah. I'm wondering what I did.
Could it be one of the other ones?
It
was like 3 folders from them.
Yeah, pretty standard. It's just
Is there like a master list anywhere of what protections are on what common allocators?
I'm sure there probably is. What is the school that has the shellfish team? Santa Cruz? No. One of the University of California's got a GitHub that has her libc version. What is possible and not possible from Malik Malvakaram, examples of it, and then what, like a bunch of notes on it. And I think that's probably your best and most up-to-date one. But first thing of note here is right at the top is a link to the version of Doug Lee's actual reference implementation that they pulled to back this one. So that one's from 2002 with a link to actually where the code is, which is the same FTP that I got it from. And as we walk through here, many of Doug's notes verbatim are still inside this file. Is this the right one? Yeah, here it is. Okay. So here's the unlink macro in UC libc. Very quick difference that pops right out at you is that there is a validation, right? If forward back is not equal to your pointer and back forward is not equal to your pointer, chain's not valid, so abort, right? Kills the program straight up. And it's very easy to find and see that that check has been made there, right? Because the macros are what are used most often for this stuff, most of the checks are performed in the macro, because you're going to have to perform the check in a lot of places if you want to perform it at all. So you really only have one place to look to see if a check is like a coherency validation check is made, and that's in the macro. So whatever macro is responsible for doing the work, that's where you go and look to see if the check has been made. Right? So pretty quick to find it if, in fact, you pull up the right file. Let's look at malloc.c real quick. This is all debugging code. Backing functions that talk to the kernel and handle adding more space either from nmap or brk. And where's their actual malloc? I'm really looking for here. Oh, there we go. Straight malloc implementation. The only difference here, if we were to diff this between the older version, is in how the fast bins are treated and how many bins there are and when it decides when to cut. You see the macros used are exactly the same. It's a direct use of most of Doug's code. And some of these macros, if we take a look through them, are going to have some validation checks, but most will not. Okay? We got 5 minutes left, so let's real fast look at libc, which you're actually running on all of your Linux computers.
No Alpine users here to speak up.
Next with muscle.
You gotta use muscle. Only 94,000 less than SSH.
That's crazy.
All right, so first thing in the comments here, ptmalloc2, written by Doug Lee, and then thread and arena support added by Mr. Moger.
Is this the Wolfram?
I think so, but I don't know. His last name is Alpha. Thanks for laughing. And you know, here's once again Doug's verbatim comment right at the top, right? Not the fastest, most space conserving, portable, or tunable. If we hop down here, you see people's addendums to it and the changes, right? So this is all exactly verbatim out of the original 1996 file that we looked at previously, despite this being a 2025 version. And where are our fast bin code? So the changes that we get in the current version, in addition to the multi-thread protection and arenas and differences in fastspins and fastspin specific threads and thread caches, is that there's actual pointer protection in this one, which means it takes a random number at the top and XORs